basically the same Wi-Fi connection, it connects right away. And it's like this, and it's not like, with the PC, you always worry that some virus will get in, that something really bad is going to happen, and everything's going to run slow or something. So it's even going more than compared to that speed. Oh, no, yeah, it's not bad. Raj gets very upset when the lecture speakers do not understand the concept. He listen in different ways. Oh, there's also the guys who don't like to do survey requests for people who are not fit for differential. You know, why do we keep asking for crap? Yeah, why? Why are we doing this? Just maintenance in this school? Just the very top things? Yeah, we need to go to benchmark. I hope he doesn't want to go into benchmark. What does he want to do with his life, He's PhD, right? Yeah. Okay. Oh, he's not touching it. No. Hi, everybody. We're going to get going because we start taping at 2 p.m. Dr. Singer is with us today for the first lecture. It's a very, very basic review of biostats. She was a fellow with us in Gen Med. She's got an MPH. She's a very busy clinician. She teaches a whole lot, and she does research in QI, QA. So it's fantastic that we've got her as speaker. I'll let her talk to you now.
All right, thanks, Walter. So today we're going to be talking about some very basic principles of biostatistics. I have no disclosures. So just a brief outline of what we're going to be covering. So first we're going to define what is this discipline of statistics. And then we're going to talk about populations and samples and why we care about them. We'll briefly talk about different types of variables. And then we'll review descriptive statistics. And then I think the meat of the lecture is talking about inferential statistics, specifically hypothesis testing and different types of errors that we can make. And then we'll talk about p-values and confidence intervals and why they matter. So I think we've all seen headlines like this in the popular press. So you can spin the wheel and then report a headline like coffee causes depression in twins, or daycare causes breast cancer in rats, and we've all been there. And you read this in the article in the newspaper, and you're like, well, last week I read something else. And it can feel pretty crazy. So hopefully by the end of the lecture and the course, really, you guys will have the skills you need to really understand whether what you're reading is due to chance or whether it's actually a real finding. So what is this field of statistics about? So statistics encompasses methods of collecting, summarizing, analyzing, and drawing conclusions from our data. Biostatistics is the application of statistics to medical, biological, and public health data. We'll be talking a little bit about descriptive statistics, which is a means of organizing and summarizing observations. And statistical inference is the process of drawing conclusions from about a population from a sample. So in statistics, we often want to ask questions about populations. And a population is a collection of all subjects of interest. And it can be however you choose to define this population. It can be all medical students in the United States, all patients aged 18 to 65 with diabetes, anyone in Africa who's had Ebola. And I've sort of graphically, visually depicted here a population of smiley faces within the circle, all different colors. So this is our population here. Many times, this population of interest is too large for a researcher to study the whole group, whether it's not feasible to contact everyone, it's too expensive, whatever the issue may be. And so instead, what statisticians end up doing is they choose a representative subset of the population, which we call a sample, to study. And there are many different types of samples, many different ways you can go about sampling a population. You can talk about random sampling, so I'm going to take every 10th person in this little circle of smiley faces. You can talk about a convenient sample. You could just take a cluster of the people who happen to be in a waiting room on a given day. So this right here is going to be representative of the sample that we've chosen of our smiley faces in the circle. And so what we try to do is we use information from the sample to help answer questions about the population. So here's our population again. And so when we're interested in asking questions about populations, we're interested in a parameter that describes that population. So in this instance, the parameter of interest for us right here is the proportion of red faces in the population. So imagine that we were unable to count all of these smiley faces, so what we did was we selected a sample from the population. It's over here. And the statistic, the proportion of red faces in the sample, is much easier to calculate. We can just count them up, 1 out of, I don't know, 9 or 10 or something. And then what we try to do is generalize the results from the sample back to the population. So I've alluded briefly to the concept of variables, which are characteristics or conditions of an observation that can take on different values. And obviously many different types of variables. You can think about age or sex or race, ethnicity, number of coffee cups per day. And usually in statistics and epidemiology, we're interested in the relationship between two variables. So we have our dependent variable, which is often our outcome or our variable of interest. And we have our independent variables, which are our exposures or our predictor variables. So let's take an example to try and put these concepts together. So a researcher is interested in the proportion of medical students who drink at least 1 cup of coffee daily. To answer this question, he randomly samples 100 medical students and finds that 50% of them are 1+ a day cup of coffee drinkers. So what's the population? Yeah, all medical students. Good. Oh, what's the sample? Yeah, someone said it. The random sample of 100 medical students. And the parameter? What's that? Someone? Yeah, proportion of all medical students that drink 1 cup of coffee. And I'll tell you, I remember population and parameter both start with P. That way you can remember they go together. And then how about the statistic? Yeah, it's going to be 50%. So in your sample, so sample and statistic, they also both start with S. 50% of your med students in your sample drink at least a cup of coffee a day. And so what you note here is the parameter is unknown, right? So we don't know this parameter, and we're trying to estimate it with the statistic. And so next, the researcher wants to know if age, gender, or level of exercise predict being a daily coffee drinker. So what's going to be our dependent variable here? Yeah, being a daily coffee drinker. And the independent variables? Great. Age, gender, level of exercise. Terrific. Good. So not too complicated. So we're briefly going to talk about the different types of data that you can encounter. So we have categorical or qualitative data. And so first we have nominal, which are when you have values that fall into categories or classes that are mutually exclusive and are not ordered. And you can have dichotomous or binary nominal data, where you only have 2 possible categories. So you can think of sex, you're either XX or XY, or, well, that gets complicated. You're either male or female, and or you can think of mortality status. That one's a little simpler. You're either dead or alive, right? Or you can think of nominal variables that have multiple categories, like race, ethnicity, or blood type. And so these can't be ordered at all, right? There's no order to blood types. A is no better than AB or O or B+, whatever. And then we have ordinal data, which is where values fall into categories or classes where order matters. And so you think about disease stage. So you can have cancer where you have stage 1, 2, 3, 4 disease, or satisfaction level. So order matters here. But it doesn't necessarily mean that the difference between stage 1 and 2 disease is same difference as you have between stage 2 and 3 disease. It doesn't have to be the same increments between these classes. And so with qualitative data, you can't really do any mathematical operation. So it doesn't make sense to add these, subtract these, multiply these. As opposed to numerical or quantitative data. So two types of numerical data. You can have discrete data, which is where data has numerical values that take on only certain whole number integer values, so number of children in a family. Or continuous data, where data has numerical values that can take on any values. So height, weight, time. They don't have to actually be full integers. And this just summarizes the types of data. And what I like here is this little arrow that goes between your numerical and your categorical data, because it reminds me to tell you that you can turn numerical data into categorical data, though you lose a lot of information by doing that. If you collected blood pressures on a whole sample of people, you could report them as 141 over 92, or you could report them as above or below 140 over 90, high or low blood pressure. But by doing so, you lose a lot of important information. So the audience participation part again. What type of data is smoking status? Yeah, nominal. And what type within nominal? What do you think? Yeah, I mean, you could think of ways that it could be both binary, smoker, non-smoker, or you could think about ever smoker, heavy smoker, light smoker. Great. And how about age? Yeah, so it could be continuous. You could also think about ways that it could be ordinal, right? You could choose, 10 to 20, 20 to 30, 30 to 40. So it depends upon how you cut the data. Great. So we're going to move on to descriptive statistics. And within descriptive statistics, we're going to talk about frequency distributions, measures of central tendency, and then measures of spread. And a lot of this will probably end up being a review. So with frequency distributions, for categorical data first, frequency distributions basically are a way to look at your data visually to understand what you have. Sorry, excuse me. So for categorical data, we can look at things like bar charts, and pie charts. So if we ask the question, what do medical students prefer to drink while studying, you can visually very easily see here in your bar chart that it's coffee, or in your pie chart that it's coffee. Continuous data we look at a little bit differently. Frequently we'll use histograms, where here we have frequency of the values on the y-axis and weight on the y-axis. And the frequencies are shown by the heights of these vertical bars that each have the same width. So most people in the sample weigh from, 70 to 80 kilos or pounds or whatever it is. Continuous data can also be represented using a box plot. And so this gives you a little bit more information here. Again, we have weight, and this middle line here is the median of the data, and we'll get into what exactly that means in a minute. And you have the ends of this central box being the 25th to 75th percentile, and then the ends of the line here really being the range of your data. When we look at frequency distributions, there are several different types of patterns that we can see. So starting in the top left, you have unimodal, where there's really one peak. You've got bimodal data here with 2 peaks. Down in the bottom left, you've got right-skewed data. So you can see this frequency distribution has a tail to the right. Can anyone think of data that might look like this? That might be right-skewed, that might have many more high values than lower values? What's that? Sorry, many more low values than high values? How so? Okay, yeah, so most people are gonna, I'm not a pediatrician, but if I remember correctly, you get it more like, more when you're younger. What else? Income is a really classic example here. So here you have the bulk of your population making money that, income that looks like this, and then you've got your 1%ers out here who are making way more. And then we have left skew data, which has a tail to the left here. So many more of your participants are having these higher values with this tail of sort of the lower values. Any ideas? Anything that comes to mind? Grades, maybe. So often we see this, that most people are clustering up here in the 80s, 90s, who knows what, with grade inflation. And then there often is this tail here that's not doing as well. All right, so to describe central tendency, there are 3 ways that we often do it. So the first is mean, which is the sum of all values divided by the total number of values. The next is the median, which is the middle value of the ordered data set. And then lastly is the mode, which is the value that occurs most frequently in a data set, and probably the least frequent measure that we use of central tendency. And so quickly how you do it, you've all done this, but you add up, for the mean, you add up all the numbers, divide by 7. The median, you put them in order, and you pick the one in the middle, and the mode, you just figure out what comes up most often. And so you can imagine why mode is sort of the least reliable for most data in terms of describing it. So for means, I've alluded to this, but the advantage is that it uses all data values, so everything is there. It can be skewed by outliers. So if you have a couple outliers and right-skewed data, you might move that mean to the right where it's not actually doing as well of a job describing your sample. The median, on the other hand, is not as distorted by outliers or skewed data, but it can ignore some of the information that's there. And the advantage to the mode is that it's pretty easily determined. You don't need to do any math. You can just look at data often. But like I have said, it ignores the vast majority of the information that you've collected about your sample. Next, we'll talk about measures of spread. So samples can have the same measures of central tendency, but very different frequency distributions. So if you look at these 3 sort of frequency distributions down here, they all have the same measure of central tendency, probably all the same mean here, but they're very different. And so we use measures of spread to describe the variability of dispersion of data. This blue data is much more tightly clustered around the mean as compared to this red data. So just to describe spread, we can talk about the range, which is going to be the difference between the largest and smallest values in your sample. And it's really easily determined, but again, can be distorted by outliers if you've got someone way out to the right or way out to the left. More often we'll use an interquartile range, which is going to be the difference between your 25th and 75th percentiles, which is not really as affected by outliers and more appropriate for skewed data. And then most frequently we'll use variance or standard deviation. So those are both measures of spread, which describe the extent to which each observation deviates from the arithmetic mean. So for variance, basically each deviation from the mean is squared and then added together, and we have to square them, otherwise your positive and negative deviations are going to cancel out. And then the standard deviation is just going to be the square root of the variance. And basically it's an average of the deviations of the observation from the mean. And so the advantage is here that we used every observation, and it's pretty easily interpreted, as we just mentioned above. All right, so then we're going to move on to inferential statistics. So inferential statistics is the process of drawing conclusions about a population from a sample. And sample data is used to determine whether a hypothesis about a population parameter is plausible. And so to do this, we generate 2 hypotheses. You're always going to have a null hypothesis and an alternative hypothesis. And your null hypothesis is always going to assume that there's no effect of whatever you're talking about, whether it's a treatment, that the placebo and the drug are the same. There's no effect in the population. And your alternative hypothesis is going to be the competing claim, that there is an effect. So to sort of make this make a little more sense, the researchers are interested in whether drug X improves mortality in patients who have contracted Ebola in the recent outbreak. They chose a sample of patients and randomized them to receive drug X or the placebo, and then they measure mean survival in each group. So if we were going to think about what the null hypothesis is in this study here, the null is going to be that the survival of the placebo group is the same as survival in the drug group. And then the alternative hypothesis is going to be your completing claim, that survival in the placebo group is not the same as survival in the drug group. And so in hypothesis testing and inferential statistics, we initially assume that the null hypothesis is true. We collect data from our sample to try and disprove that null hypothesis. And we are able to reject the null in favor of our alternative only if there's strong or convincing enough evidence against the null hypothesis. And later on in the talk, we're going to get into what exactly do we mean by strong enough or convincing enough evidence. And then we have two conclusions in our hypothesis testing. Either we're going to reject that null hypothesis or we're going to fail to reject that null hypothesis. So let's go back to our Ebola example for a moment. So we've got a 2x2 table here. And so here we have the population, or the truth. And this is actually something that we don't know, but let's pretend that we did. So there are two conclusions here. The survival in the placebo group is the same as survival in the drug group, or survival in the placebo group is different than survival in the drug group. And we've done our hypothesis test here, so we're going to fail to reject, or we're going to reject. So if the survival is equal, and we fail to reject that null hypothesis, we've made a correct decision. And if the survival in the placebo and drug groups are not the same, and we reject that null hypothesis, we've also made a correct decision. There are two types of errors that we can make in these lighter shaded boxes. So if survival is equal in the two groups, and we reject that null hypothesis, we've made an error, and we're going to call that type of error a type 1 error. And if survival in the placebo and drug group is not equal, and we fail to reject, then we've made a type 2 error. And so let's put this into words for you. So a type 1 error is when we reject the null when the null is actually true. So this is concluding that the treatment works when in fact it's no different from the placebo. And by convention, we say the probability of making a type 1 error is going to be alpha. And a type 2 error is when we fail to reject the null when the null is false. And so this is when we conclude that the treatment is no better than the placebo when the treatment actually has benefit over the placebo. And also by convention, we say that the probability of making a type 2 error is going to be beta. And it brings us to sort of a complementary concept, which is called power. And so power is the probability of rejecting the null hypothesis when it's false. So this is what we want to do. And the probability of not committing a type 2 error is going to be 1 minus that beta. And so, ideally we want our power to be 100%. Often we end up settling for something closer to 80 to 90, and we'll explain why that is in a little bit. But there are several factors that are going to influence your power, or so the sample size is important. Power is going to increase with larger sample sizes. Power also is going to increase as your variability decreases. Effect of interest, or sort of treatment effect, is also important. Power is going to increase with a larger treatment effect size. And your significance level, or your alpha, is going to impact your power. Power is going to increase with a larger alpha. And so to look at this sort of visually here, we've got two graphs. We'll start with the one on the left. So on the bottom is sample size, and on the y-axis is power. So let's first look and see what happens with sample size. Let's stick to one standard deviation. So let's pick this standard deviation of 5. So you can see as your sample size increases from 50 to 100, your power is also going to increase. Then what happens with variability? Well, so let's stick now to one sample size, we can see that as our variability decreases, so the standard deviation goes from 6 to 5 to 4, our power is going to increase. Next we can look at effect of interest. And so again, sample size is on the bottom and power is on the y-axis. And so for a sample size of 250, as your effect of interest gets larger, your power is also going to get larger. And then we can look at alpha, or significance level. So as your alpha increases from 0.01 to 0.05, you're going to see that your power also increases. So let's go back to this pretend trial that we're doing here. And so let's say the results of that Ebola trial show us that the mean survival in the placebo group is about 5 days, and the mean survival in our drug group is closer to 10 days. So how can we explain this difference in survival? So we hope it's a real difference between the placebo and the drug, but it could also be due to random variation or chance, that the observed difference that we saw just happens to be due to coincidence. It could also be due to sample error or bias, that the sample that we've chosen is not representative of the population for any variety of reasons. We're not really going to get into this sampling error or bias in this lecture. So let's do an experiment here to understand a little bit about some of the chance. So statistical tests we've talked about are designed to determine if the observed difference between the groups was likely due to chance or in fact a real difference. So we've got this coin. Our null hypothesis is that the coin is unbiased, and our alternative is that that coin is biased or weighted in some way. So we could flip that coin 10 times, and we could get any variety of number of heads. We could get 5 heads, 5 tails, 6 heads, 4 tails, 10 heads, 0 tails. And so if we were to look at a frequency distribution of the probability of the number of heads under the null hypothesis, that the coin is unweighted or not biased, you can see that most frequently we'd expect to get 5 heads. But a little less than 25% of the time. It wouldn't be crazy just by chance to get 6 heads or 4 heads, maybe even 3 heads or 7 heads. But when you get down to 10 heads or 0 heads, if that null hypothesis is true, if our coin is unweighted, it's going to be exceedingly rare to get 10 heads, 9 heads, 1 head, 0 heads. And so remember we said earlier, we're able to reject our null in favor of our alternative only if there's strong or convincing enough evidence against the null. So are we willing to reject the null and conclude that the coin is biased if we get 7 heads? So let's go back here for a sec. So 7 heads, that's 12% of the time. That's not all that rare. Well, what about if we get 10 heads? Yeah, probably. That's really going to be a rare occurrence. Oops, wrong way. So the question that I'm asking is, how unlikely does the outcome have to be before we're comfortably able to conclude that it was not due to chance alone? And it's another way of asking, what is the chance of making a type 1 error that we're willing to accept? And so this is our alpha. And so what we do is we specify this alpha, the chance of type 1 error that we're willing to accept, prior to collecting our data. And typically, you'll see in the medical literature, we choose an alpha of 5%. And this means that we'll reject a true null hypothesis about 5 times out of 100. And using a smaller alpha is going to increase your beta. So just a recap here of what we've done. We've talked about defining, in a recap of inferential statistics or hypothesis testing. We've defined our null and alternative hypotheses. We have set alpha. We have collected data from our sample. The next step is to actually perform the statistical test. And that's outside of the scope of what we're going to be talking about here. This is, a flow chart of not all, but of many different types of statistical tests. And the reason that I spent a little bit of time at the beginning of the lecture talking about numerical and categorical data and making numerical data into categorical data is because really the type of data that you're collecting is going to determine what type of statistical test that you do. And that's really all that you need to take away from this chart. So that statistical test that your statistician has helped you to choose is going to give us a test statistic, which we can then compare to a null distribution to determine the p-value. And our p-value is the probability of obtaining our results or something more extreme given that our null hypothesis is true. And when that p-value is less than our pre-specified alpha, we can reject the null hypothesis and conclude that the results are significant at the alpha percent level, so usually the 5% level. So let's look at a couple of examples. So let's say we did our statistical test and it gives us a p-value of 0.01. So our interpretation of that p-value is that if our null were true, we'd expect to get our results, or something more extreme, 1% of the time. In other words, what we observed when we got our data was something that is very unlikely to occur by chance alone if that null hypothesis is true. And since our p-value is less than our alpha, we're going to decide to reject our null hypothesis. And we're going to conclude that at the 5% level of significance, there's sufficient data to conclude that survival in the treatment group is not the same as survival in the placebo group. On the other hand, say we did that statistical test and we got a p-value of 0.25. And so our interpretation of that is that if the null were true, we'd expect to get our results or something more extreme 25% of the time. In other words, results like ours would occur 25% of the time if the null hypothesis were true. And since 25% is going to be bigger than our p-value of 0.05, we're going to fail to reject the null hypothesis. And we're going to say at that 5% level of significance that we've chosen, there's insufficient evidence to conclude that the survival in the placebo group is different from survival in the drug group. The next concept that we can talk about are confidence intervals. And a confidence interval is an estimated range of values which is likely to include the population parameter, whatever that parameter is, whether it's a mean, or odds ratio, a risk ratio, hazard ratio. And so it's usually represented as a point estimate, and then the upper and lower bounds of that 95% confidence interval. And our practical interpretation here of a confidence interval is going to be that we're 95% confident that that true population parameter lies between upper limit and lower limit. And depending upon sample size, the confidence interval depends upon sample size, variability of the data, and the significance level that we've chosen. And if a confidence interval, if the upper and lower bounds of that interval don't include the null value of a zero effect, then the results are statistically significant. So we're now talking about a second way to show if data is statistically significant. So p-values and confidence intervals are complementary concepts. So p-values are going to give you that statistical significance. If your p-value is less than alpha, it's significant. If it's greater than alpha, it's not. Confidence intervals are going to give you statistical significance and some information about the size and the direction of the effect. So we can go back to this Ebola example. We get a p-value, and we know that our p-value is less than alpha, so we're going to reject the null. A confidence interval is going to tell you a little bit more. So you're going to get your hazard ratio for survival, and you're going to get upper and lower limits of that confidence interval. And since it doesn't include the null value of a hazard ratio of 1, we can reject the null hypothesis. But we can also tell from this that we're 95% confident that that true hazard ratio lies between 0.43 and 0.57. A lot more information in this confidence interval than in a p-value alone. So let's look at an example here. This is from Annals about a year ago. And so let's say that a group of these researchers were interested in whether corticosteroid injections or manual physical therapy are better treatments for shoulder impingement syndrome, which is just basically, you can think about it as shoulder pain, you can't move your shoulder very well. So these authors took 104 patients and they randomized them either to get steroid injections into the shoulder joint or to get manual physical therapy of their shoulder. And a change in their pain score over 1 year was measured. So just to review, what's the null hypothesis here? I hear a lot of whispering, hopefully whispering that pain is going to be the same in both the steroid injection and the manual physical therapy group. And the alternative hypothesis? Yeah, it's different. And then these authors set alpha, as just about everyone does in the medical literature, at 0.05. And then the authors perform the statistical test, and there's a lot of text in the article about that. But let's jump to the results. So here we have, at 1 year, which is what they said, you have the mean pain scores in the two groups and the difference. And you can see the p-value is 0.7. So we're going to fail to reject our null hypothesis. And we're going to conclude that there's insufficient evidence to say that steroid injections are any different in terms of, when compared to manual physical therapy, in terms of this spotty pain score. We can also take a look at the confidence interval for the mean difference, which is from -6.3 to positive 9.4. And so that included the null value. So we can reach the same conclusion by just looking at the difference. And we can reject the null hypothesis. So the researchers also here, it wasn't their primary outcome, but they also asked whether the use of primary care provider visits after the initial treatment, whether they got the steroid injections or they got the manual physical therapy, differed between the two groups. So here we have PCP visits after initial care. And you can see that there are more PCP visits in the injection group compared to the physical therapy group. And this little asterisk here, sorry, I cut it out, but that basically is telling you that the p-value was less than 0.05, so we can reject the null and conclude that there's sufficient evidence to say that PCP visits are not equal for steroid injections and manual physical therapy for impingement syndrome in this sample. So again, our 95% confidence interval is going to give us a little bit more information, and it doesn't contain the null value, which also tells us that we can reject the null hypothesis. And lastly, we're going to end with a really important concept here, which is that of clinical significance. So statistical significance, which we've been talking about with p-values and alpha and confidence intervals, really has to be distinguished between clinical significance when you're a clinician. So even a really small difference that's not clinically meaningful can become statistically significant if your sample size is large enough. So for example, say we reject the null and conclude that the difference in survival between the placebo and the drug group were a matter of hours. So it's statistically significant, you live 12 hours more, probably doesn't make a difference, right? That one's an easy one, but if if it was a cancer treatment and they told you you're going to live a month longer, that's a little bit complicated. A year longer, is that worth it? So this concept of clinical significance plays a really important role. It's not just all about p-values. And I like this picture to help, bring home this point. So R is what you set as your clinical relevance limit here. So it could be, if this were a blood pressure study, say you thought 5 millimeters or 10 millimeters of mercury are different, or a month of life, or reducing your pain score by 10 points, whatever it is, that's going to be your R. And then 0 here is going to be your null value. So if we look at choice A up here, this is an example of what results might look like if they're statistically significant, but not statistically significant and also not clinically relevant. So your effect estimate, which is represented by this horizontal line here, doesn't go past your R here, your clinical relevance limit. And then also your 95% confidence interval is overlapping with the null value. As opposed to, this is the type of study that we really want to see. This is what makes an impact on clinical care. Data that's both statistically significant and clinically relevant. So your effect estimate is all the way out here past your clinical relevance limit, and then your 95% confidence interval does not overlap with your null value. So this is sort of what we don't want to make clinical decisions on often. So when you have statistically significant data, but things that are not clinically relevant. So your effect estimate is definitely below your threshold that you've set for clinical relevance, but it's statistically significant. So this is the hours or minutes to live, or whatever you want to call it. And then this is things that you don't necessarily know what to do with, right? You say, oh, great, your effect estimate looked like this is that this is going to be relevant data, but your confidence interval overlaps with your null value, and so it's not something that's statistically significant. And that looks like we're early, but that's about all that I really wanted to cover today. So we've got some time for questions. Yeah. Yeah.
Is it possible that we're missing a lot of things that could potentially be clinically relevant that fall very close to 0.05, but that don't quite make it, like just 0.55?
Yeah, that's a terrific question. So the question was, so you've told me that we're setting this alpha at 0.5. what happens when it's 0.51, 0.6? You know, are we missing things that are potentially statistically or clinically relevant with that threshold? And yeah, and I think it's where judgment comes into play to a certain extent. The 5% is something that, you know, we do by convention. Other fields will use 0.1%, where perhaps your choices are not as high stakes as we are. So sometimes people will use 0.1, but you're right. 0.5 is somewhat arbitrary. I don't know if you have anything to add to that.
Yeah, since we've got time, there are a couple of wrinkles attached to that. The first thing that gets people confused is the fact that when we go into biostats, we actually have a good hypothesis we're testing, which is we're reducing mortality with the treatment for Ebola, in her example. But actually, when we run the statistical test, we do a two-sided analysis. Okay, so the p-value is going to be a two-sided. It actually takes into consideration the possibility that you also increase mortality with a new treatment. And that is important because we've had many instances, including the very recent past, when people with best intentions and with very good basic bench background went into testing a hypothesis and actually ended up harming patients. So we do test for both benefit and harm all the time. Two-sided hypothesis testing is actually the rule, not the exception. Okay, so you can get a p-value that's less than 0.05 because you're actually increasing mortality. And that actually has to do with your question, because when you're dealing with harm, you may want to pay a whole lot of attention, even if the p-value is 0.07, if you're increasing the risk of death. So it's always a matter of having clinical judgment attached to your statistical finding. So that's very important. Actually, the cutoff point of 0.05 for p-values was created in the 1930s when Alban Fisher was first working in inferential statistics. And he pulled the number out of the hat, and we've been stuck there ever since. So the most important thing to remember is that we always want to look at things as clinicians, and we need to try to establish whether there is a trend that may be important to us, and maybe we need better power and we need a larger study to achieve a p-value less than 0.05 next time, or no, if there is the possibility of harm, maybe we need to stop right there and then and not continue to try and get a p-value less than 0.05 because we don't need that to stop causing harm. Is the concept of confidence intervals clear to you guys? Did you understand what it means? Well, it is the range of values. We usually use 95% confidence intervals. So it's the range of values at which you are 95% confident that the true population value resides within. Okay? It doesn't represent the true probability of the finding. That's a completely different business. That's very complicated, and that's why we keep using the word confidence. Okay, I don't want to get into discussion between confidence and probability because actually books have been written about it, and you need to understand Bayesian theory at a pretty advanced level to actually go into the nuances of that conversation. Yeah? You mean the confidence interval? Yeah, the confidence interval, essentially the best way to imagine that is when you think of the bell curve. So you can make it similar. Do you guys remember what is contained within two standard deviations to the right and to the left? Right. So that's essentially your confidence. It's a confidence distribution for a bell curve for your estimate. So not every statistic in medicine or in biostats has that type of bell curve distribution, but many of them do, and that's actually an easy way to picture your confidence estimate. Just imagine that you get the point estimate, the value you're reporting for example, the relative risk right in the middle, and then the confidence interval will demarcate your two standard deviations to the right and to the left. That's a very easy way to picture it. So the most important thing to remember is that there is statistical significance and there is clinical significance. And it's always important to look at clinical significance from the point of view of the patient and from the point of view of society. And keeping both perspectives in mind is extremely important when you go into clinical practice. Any other questions? That's it? All right. So I told you guys about the EBM glossary. Did you see that? There are actually definitions for p-values and for confidence intervals in there. That's a quick reference guide for concepts like this one. And if I made a mistake in any of the definitions, just let me know. Because Wikipedia can correct me. Do you guys prefer to take a quick break or keep going? Whatever works for you. Keep going? All right. I'm sorry, break? Okay, so we'll take a 2-minute break and we'll do it.
Right. And it says replace the same computer. Yeah. And it's like fail free thing. Oh, no, you're absolutely right. The fail free thing is so let's crucial item of business will be is whether you have a true negative study or you have information power. Because it's possible that you want power to detect a difference that clinically means. So oftentimes investigators will go into a study with limited budget. And we may not be able to do the research we need there to prove that there is a difference that may be clinically meaningful, but it's kind of more than what we were powered to do. And that, two items are important. Number one is you can do meta-analysis, and one of our sessions is going to be about meta-analysis. So essentially meta-analysis is put together results from different papers, and individually we have a file, but when you aggregate them, if they are similar enough, you can narrow that sample down to whole results. And there are many scholars of meta-analysis. So meta-analysis is one, and the other one is if you really think that's important to advocate for the real people, that will give you the right. And oftentimes people will do that and they say, this is a good thing, or this study was really important, the one that you look at let's put some correction because I think there is a specific
All right, let's get started, guys. Any problems with coursework or accessing data online? Not that I know how to solve the problems, but I can pass on the the message to the right people. Any trouble accessing data? Were you able to open up the homework file for next week? It's small group session, so just, again, it's not a test, but if you answer the questions, then you're going to be ready to have a group discussion and, you know, ask your preceptor questions. One of the things about this entire business of biostats and EBM is that there is no perfect textbook. You know, people who want to do this, like residents, you know, they come to me all the time and say, is there a good textbook? And I tell them I'm still writing it. There is, you know, I've read like 20 different textbooks, and I get a chapter from one and half a chapter from another. I listed a whole bunch of electronic resources in that memo I sent you guys, and which one you prefer, it actually depends on your level of prior training and your personal preferences. But the opportunity to actually talk to somebody who not only has a degree in stats or epidemiology and also is a clinician is great, and those are the preceptors for the small group sessions. The other thing is I just got told about a minor mistake in one of the slides. I'm going to be correcting that. So please keep your eyes open, because nobody's perfect and we all make mistakes, and we keep on improving thanks to open sourcing. So feel free to contribute. And, you know, just write me. The only thing I read all day long is my Columbia email, so just write to me if you have any comments or suggestions. All right. So no conflicts of interest. Relative risk. You're going to hear a whole lot about relative risk, and this is in its simplest iteration. This is the easiest way of doing this. This is going to be all over step 2 and step 3. The interns hear about this all the time because we get them ready for step 3. This is estimated in a very straightforward manner. All you need to know is how many people got assigned to each one of the 2 randomization arms, and then you need to count the number of events in each one of those 2 groups. So you just divide event rate in the intervention arm over the event rate in the control arm, and that will give you the relative risk. Again, event rate is just the number of people who had the event over the number of people in that arm. So if you're looking at a study on mortality, you just need to know how many people got assigned to treatment A or treatment B, and then at the end of the entire follow-up, how many people died in treatment A or treatment B. So the idea, the goal, is that mortality should be lower in your intervention arm as compared to your control arm. And usually intervention is your new treatment. And it can be against placebo if there is no known treatment, or it can be against the standard of care if we already have a treatment. This is not a perfect estimate, but it's a very easy one to obtain and understand, and that's why there is so much emphasis on you guys really remembering how to obtain this when you read a journal article, okay? There may be circumstances, and I'm going to be quickly describing some of the most important ones. There may be circumstances in which the relative risk is not a perfect reflection of risk, but usually, in 99% of the times, it's a pretty good reflection of treatment efficacy. So that's why we insist on this. So again, it's just event rate in the treatment arm over event rate in the control arm. And like for anything else we do in biostats, you are actually able to obtain a confidence interval for this. There are many apps you guys can use for this. There's one that's actually pretty good, MedCalc. You can get the basic version for free. I think the pro version is like $199, so it's ridiculous. And there's an evidence-based medicine portion of the app. And if you just enter the numbers for events and sample size in each one of the cells, you're going to get your relative risk estimate with the usual approach to estimating 95% confidence interval. You will be required when you take different tests, like step 2 and 3, to do this by hand, but it's fantastic to actually do it by hand and then cross-check your results using the app. All right? So what are the limitations when you use a simple statistic like this one? Well, first of all, you do not adjust for how complete the follow-up was in the 2 different groups. And I'm going to give you a very straightforward example of that in a second. And it also ignores what you heard about the other day, which is confounding. So it does not take into consideration the distribution of important variables that may be also associated with the outcome in the two treatment arms. So, for example, if you are randomizing a small number of people in a cardiac study and you just by chance end up with very high-risk patients in one arm, like people with very low left ventricular function, you may have higher mortality in that arm just because of that fact and not because of anything related to the treatment itself. So confounding is not being considered by relative risk in this calculation. So the other thing you're going to be hearing a whole lot about is the number needed to treat. And again, this is all over step 2 and step 3, and then boards of internal medicine if you go into medicine. The number needed to treat is the number of people you need to expose to a treatment to prevent one bad outcome. It's the exact opposite of the number needed to harm. Okay? So let's start by talking about how it is estimated. You first need to do the absolute risk reduction, and that is simply the event rate in the control arm, the event rate that you have at baseline with the standard of care, and you subtract from that number the event rate in your treatment arm. So again, event rates are just estimated in the same way as before, number of events over sample size in each arm. And our hypothesis is that the event rate is higher with the standard of care, and that's why we're subtracting from that number the event rate in the intervention arm. We expect the event rate to be lower in the intervention arm, so we subtract that number from the event rate in the standard of care. That difference is an absolute risk difference, and it has to be kept in decimal point notation, meaning 0.2 something, 0.3 something, not 30% or 20%, and you do 1 over that, you invert it, and you get the number needed to treat. So the only thing you need to memorize here is how to do the absolute risk reduction. Again, event rate in the control arm minus event rate in the treatment arm, and you do 1 over that, and you get the number needed to treat. Just like with all other statistics, you can estimate the 95% confidence interval, all the apps, all the different programs that you can find online, Java calculators, you know, if you use SPSS, SAS, whatever, you're going to get 95% confidence intervals for the number needed to treat. There are ways of estimating this from other survival statistics, like the hazard ratio, which I'm going to discuss in a few minutes. But the most common notation is this one and the one you guys are expected to remember. And why do we care so much about it? Well, we care so much about it because it gives us an idea in terms of the societal impact of the intervention. If you remember from number needed to harm in Dr. DeMiguel's talk, if you have a small number needed to harm, that means that you've got something really bad. You expose a tiny number of people and you get one bad event. If the number needed to harm is huge, then it's not that bad. You need to expose a whole lot of people to the bad exposure to generate one bad outcome. This is the exact same principle applied to therapeutics. If you have a tiny number needed to treat, that means you have a wonderful treatment. And the example of that is defibrillators in people with ischemic cardiomyopathy and low ejection fraction. The number needed to treat is actually less than 25 over 1 year. That means you put in 25 defibrillators and you save 1 life in 1 year. That's remarkable. So it's the same concept, and the absolute risk difference is the same. So in one case, we call it the absolute risk reduction because we're reducing risk in this case, and in the case of harm, we call it the absolute risk increase, but it's the exact same concept. So the relative risk reduction is important because this is what most patients understand. We have very few patients who have background in mathematics or physics or things that allow them to think about numbers. So we prefer to talk about this because everybody understands when something is 20% off in a cell. And this is actually that concept. You just take the relative risk and you do 1 minus the relative risk, and you get the relative risk reduction. And we usually use percentage estimates because they are easy for everybody to understand. So you can explain to a patient that you can reduce her risk of dying by 20% if you give her a treatment. And that's very easy to grasp. People don't understand numbers needed to treat. If you give my average patient in the clinic, the number needs treat of 25, they think that 24 people die and 1 survives. So we usually use the number needs treated to harm for our discussion, for public health discussions, and we give the relative risk reduction to our patients. So what are the limitations of accrued relative risk? Well, let's just do a very simple example of a study with 100 participants in each arm, and at 3 years, you have 10 deaths in the intervention arm and 20 in the control arm. So, like I said before, you've got here your relative risk estimated through event rate in the intervention arm over the event rate in the control arm. All right? That's pretty straightforward. 100 people, the denominator in both cases, 10 deaths here, 20 over here, so you get 0.5. That's your relative risk. What is the relative risk reduction for that? 50%. 1 minus 0.5, 50%. That sounds great, right? Well, if you look at the data more closely, you realize that all 80 people who survived in the control arm actually came back to see you near the end of 36 months. But of the 90 people who you thought had survived in the intervention arm, 20 had a follow-up time of only 2 years. No information after that. So how confident are you now about that relative risk of 0.5 or relative risk reduction of 50%? So the crude relative risk is estimated, assuming, in this case wrongly, that all survivors had equally long follow-up times. And how do we take care of this? Well, there is a very common method in statistics known as censoring. Censoring means that you take information from somebody for as long as they are known to be alive and are giving you follow-up data, but whenever you lose contact with that person, you drop that person from the denominator, meaning you don't use their information anymore when you're trying to estimate the importance of a new event. So there are other types of censoring. People who do epidemiology actually love complicated stuff, and you may get told about left censoring, right censoring. Well, the one that actually matters, because matters in the studies you're going to see the most, which are randomized controlled trials, is the type of censoring that takes place when you randomize people into treatment arms and you follow them up and you lose touch with them. And at that point in time, you should censor them. In that way, when you censor people, you'll avoid the mistake of overestimating benefit in our previous example. So again, censoring means that you keep them in the denominator for the event rate only for the time her or his status is known. Once you don't know about their status, you have to drop them from your estimates. So we use relative risk when we quickly look at the results of a clinical trial, but the most common survival statistics, when you pick up a New England, when you pick up Annals of Internal Medicine or BMJ, Lancet, Circulation, whatever you happen to enjoy, the two most common statistics you'll encounter are the Kaplan-Meier curves, the log rank statistic, and the Cox proportional hazards regression. So the analogy I make to people at this point in time is that your relationship with these statistics has to be like my relationship with my car. I don't know how to make a car, I don't know how to fix it, but I know how to drive it. So the idea here is that you should know how to deal with the statistics and their meaning and when they are reliable or not. If you want to learn how to actually estimate them, that's a different course, and if you have any projects for which you're trying to do that, I would be delighted to give you a brief consultation because I've done a whole lot of that, but this is not the scope of this lecture. So Kaplan-Meier curves. This is a very common graphic. How many of you have looked at a recent New England Journal of Medicine, for example? Did you look at a clinical trial? Like when they say original research articles, 75% of them are RCTs, and they all have a figure like this one. So I want you guys to be familiar with the Kaplan-Meier curves. I want you to understand what they mean. So they have these little lines going down from 100%, and they represent, each line represents the cumulative probability of survival. Again, it's a probability of survival at that point in time, depending on which treatment arm you're on. It's not the actual actuarial survival, it's a probability of survival. And obviously, it starts at 100% when you're enrolling in study, and this is event-free survival. Okay, this happens to be from a study comparing two treatments for coronary artery disease, one that did stenting plus medical therapy, and the other one just medical therapy alone in people with chronic stable angina. So obviously, everybody starts at 100%, and then slowly you start having events. In this case, it's myocardial infarctions and death. So as time goes on, a whole lot of people over 5 years of follow-up will be having events. And what type of statistics will accompany the Kaplan-Meier curves? Well, usually you're going to get this, the hazard ratio, which is like the relative risk, and I'm going to explain that a little bit more. And you get a p-value for this, the log rank test. So let's concentrate on the Kaplan-Meier curves at this point in time. The y-axis in its best format looks like this. It goes from 0 to 100%. The New England and most of the first-tier journals do not accept a truncation, a y-axis that goes from 60 to 100, for example, instead of 0 to 100, because if you had that, what will happen? If instead of having 0 to 100 here on the y-axis, on the vertical axis, you cut that off and you started at 40 or 60% and went from 60 to 100%. Absolutely. It exaggerates the divergence between the two lines, and you can have a difference that's not clinically that impressive, but the pharmaceutical company coming to you with a glossy brochure at the time the rep is coming to give you free lunch will give you a graphic that's truncated, and you're going to look at it and you're going to say, wow, that's a wonderful difference in event-free survival. And it's just created by that illusion of truncating the y-axis. So this is not a problem for the good journals because they don't accept that anymore, but there are many second-tier journals, and nowadays there's an explosion of online publications that all get indexed in PubMed for some reason, and that can happen. So you need to pay attention to that. And then over here, you have time on the x-axis. And usually you'll have years, but you may have months. Sometimes people will plot this by the number of events that take place, but this is the most usual format you'll see. And at the bottom, you'll have the numbers at risk. The numbers at risk are the number of people who gave you that length of information for follow-up. And initially, you had 472 people in one arm and 459 in the other. Do you have any idea why you only have 40 and 59 at 5 years? Speak. Yeah, censoring, yeah, very good. But why? Censoring why? Meaning the patient didn't come back for the follow-up. Okay, well, in this case, there was no attrition. People were contacted whenever the investigators wanted to contact them. Yeah, obviously, people who are already dead or had an event are not contributing data anymore. They were taking off the denominator, but in this case, you didn't have that kind of mortality rate or event rate. So what else is going on? Because you only have 40 and 59 at 5 years. This is pretty common, by the way. Explain. Perfect. Why? There you go. Perfect answer. That's it. That's it. Do you understand what he just said? You recruit people. You know, this is the second time over 5 years that I get the right answer right away. So the thing is, you recruit people over a long period of time, and you start the follow-up the very next day. And some people contribute a whole lot of information, but some people only contribute a couple of years because they got enrolled very late. And you have a limited budget. You have to stop calling people sometime. And those 40 and 59 were people who enrolled very early on, and obviously did not have an event up to that point in time, and therefore they contributed a whole lot of information. In other words, when you're plotting the Kaplan-Meier curves, you're pulling everybody to time zero. Time zero is time they were randomized into the study, not time zero for the first day you recruited somebody. Okay? Very good. So why do we get that number? What's the intention of the editors of the New England when they require that number below your x-axis. By the way, if you go to the New England 1990s, that number is not there in most of the cases. So it became a requirement. Do you know why? What are we looking for? So think of the confidence interval we were discussing before. Think of what happens to the confidence interval when the sample size gets smaller. Right. This is the same. You have much less confidence in the curves as the number of people in the denominator gets smaller. So in other words, if you see a divergence only when the numbers are tiny, you're not going to have a whole lot of confidence in that portion of the curve. So it's a sort of a surrogate for your confidence in that portion of the two Kaplan-Meier curves. Okay? So in this case, they had pretty decent numbers all the way down to 4 years. The numbers dropped at 5 years. So what is this hazard ratio telling you when you have that confidence interval? So the null value, when the two event rates are the same, is a hazard ratio of 1, just like relative risk. So you go from below 1 to a value higher than 1. So what is that telling you? That you're not certain at the usual p-value of less than 0.05 that there is a significant difference between event rates between the two arms. And that actually coincides with a very non-significant p-value from the log rank statistic. See that? Okay. So this is just very quickly so you guys can understand how we generate this curve. So let's say you've got 100 people in one arm, like we were discussing before, and you have 3 deaths in your first month. So what is the probability to survive in the first month? 97%, right? So that's a way you can plot the first step in the Kaplan-Meier curve for that group of people. And the next month, you have 1 death. 2 people are lost to follow-up. You call them, you can't reach them, they moved back to the Dominican Republic, they left no forwarding address, you're in trouble, you don't know what to do, you try contacting family members, they don't reply. So now you have 1 death, and how many people do you have in your denominator now? So 3 people were gone, right? Now, 2 are lost to follow-up. What do? As we said before, censoring is taking them out of the denominator. So now you have a denominator of 95, right? You have 1 death, so your numerator is 94. So what's your probability of surviving the second month if you were alive at the end of the first month? 99%. So how do you plot that? Do you go from 97% up to 99%? So what principle do you apply? Well, Kaplan and Myers said unless you have a suicidal pact, the probability of somebody dying in the first month has little to do with the probability of somebody else dying in the second month. In other words, as a group, the probability of an event in each month is independent from each other. And you guys know how to estimate the probability of 2 independent events taking place, right? So what is the probability that you'll get tails twice when you toss a coin? 0.5 times 0.5, which is 0.25, right? You multiply them. So it's the same principle. We multiply the probability to survive in month 1 times the probability of surviving in month 2, and we've got the cumulative probability to survive in both. That's why I said before, what we plot in the Kaplan-Meier curves is not the actuarial survival, it's the probability of being alive. All right? So that's the solution. Multiply 97 times 99, and you get 96%, and it keeps going down. Believe it or not, when I started doing research, I actually did a couple of Meier curves by hand. Thank God now I have software to do it for me. And actually, it's much better than this because when it's generated by software, the time variable can vary by hour, day, week, or month. You don't need to do it at regular steps like this. You don't need regular intervals anymore. Okay? Very good. So that's Kaplan-Meier curves. Remember again, y-axis shouldn't be truncated, and the mean of number of risk will it will give you a sense of the sample size, and therefore it will give you an idea as to how much confidence you can put on that portion of the curve. The log rank test is a comparison in the median survival times. So you have treatment A and treatment B, and you're comparing the median survival time. Actually, the way you do it is that you estimate at each point in time what the expected event rate is if both groups are having the same risk, and then you do the ratio of expected to observed events. You don't really need to memorize this. There is no point in doing that. This is just a frame of reference because in the future you will encounter a report for the log rank statistic over and over again, and I just want you guys to have some sort of familiarity with where it's coming from and what it means. The easiest way, from my point of view, the definition that I usually go for is that the log rank is testing the difference in median survival between the two groups. Okay? When people ask you, because there's always somebody who wants to know how it's done, so you can say to that person, well, I look at the observed event rate and I get a ratio of expected to observed event rate, and I compare that between the two groups. All right? So there's a value for that very few people really can understand. You need to be a mathematical genius for that, but you get a p-value. And the interpretation of the p-value is the same as we do for everything else. If it's less than 0.05, we say there is a statistically significant difference in median survival. And if it's greater than 0.05, we say there isn't. So you either reject the null hypothesis or don't. Now, what's the beauty of the Kaplan-Meier curves? Well, like in the example we just did, you do censor people. You take them out of the denominator. So this is better than the relative risk when it's estimated crudely by just looking at events over sample size. Okay? So the log rank test and the Kaplan-Meier curves adjust for censoring, which is a good thing. But the one thing that it cannot do is adjust for potential confounders. Again, if you have a small trial and you're not lucky and you get people with higher risk because of another variable in one of your arms, neither the Kaplan-Meier curve nor the log rank test will be able to adjust for that. You need something else to do that. And why do we care? Well, again, as I said before, if you have a small RCT, randomization is guaranteed to eliminate confounding only when you have a large sample size. If you have a small number of people being randomized to each one of the two treatment arms, you may have, just because of poor luck, a distribution that is imbalanced for something that's important. So I already mentioned to you guys the possibility of having people with a very low left ventricular ejection fraction in one of the two arms, and the fact that your relative risk may be not reliable in that situation. So this is why you guys are going to be seeing a whole lot of the hazard ratio. The hazard ratio was created by a guy called David Cox, Sir David Cox. He created a regression model that looks at hazards. Hazards are risk per unit of time. So what he said is, if I'm getting information for periods of time for each participant, but not every participant is giving me information for all possible periods of time, what I need to do is I need to create a method that will predict the probability of people being alive or not, having an event or not, depending on treatment arm at each period of time. And obviously, he wanted to do censoring. So it's a sort of regression, well, it is actually a regression model that takes into consideration your risk for having an event in the next period of time, provided you survive it this one. So what's the beauty of this? Well, first of all, like the Kaplan-Meier curves and the log rank statistic, it uses censoring. So that's very good. But it also allows you to adjust for confounders. So you can actually enter the information for left ventricular ejection fraction into your Cox model, and your adjusted hazard ratio will take that into consideration. And the good news is that the program will give you both the unadjusted and adjusted hazard ratio, and you'll get to see whether they differ at all or not. Because maybe left ventricular ejection fraction did not matter at all, and the adjusted and unadjusted look exactly the same, or maybe it did. Somebody the other day had a question about something that's present at the beginning but then absent, or vice versa, something, a confounder that changes over time. Well, nowadays we've got models for COGS that actually allow us to enter that kind of variable. It's something we call the time-varying covariate. It's actually pretty straightforward to enter. These are lines of code that have been written for decades, so they're not a mystery. So something that used to be extremely complicated now is extremely straightforward if you know what you need to do. So the other thing you can do is you can test for something known as interactions. This is something we didn't discuss yesterday when we were talking about confounding. Interaction is a different thing. A confounder, again, is a third variable that is associated with the exposure and is independently associated with the outcome, but it's not in the pathway. So the usual example I give for that is when people did, believe it or not, write papers about the fact that coffee drinking was associated with coronary artery disease, with having a heart attack. And those days, people who drank a lot of coffee did a whole lot of smoking, and they did not adjust for smoking. So that's your confounder. Smoking is associated with coffee drinking, and it's actually the cause that people were having heart attacks. And when you put that confounder in your model, there is no association between coffee drinking and heart attacks anymore. Okay, that's a confounder. Interaction is something altogether different. In interaction, you don't need an association between exposure and the confounder. Okay, there's no need for that. What the interaction means is that the third factor will change the way the exposure is associated with the outcome. And there's a very common clinical example of that. If you've done any type of family planning counseling, you know the questions you have to ask a young lady before you give her an oral contraceptive pill. So what's the most important question you have to ask her? Smoking history. Smoking. Smoking, if present, fundamentally changes the risk that she'll have a venous thromboembolism, meaning a deep venous thrombosis and or pulmonary embolism. And that's not a trivial item. Okay, it actually goes up, depending on the study you're looking at, by 5 to 20 times, which is probably related to genetic background and the severity of smoking. But that's an interaction because there is no association between taking the pill and smoking, but smoking fundamentally changes your risk of having a DVT or a PE. That's something known as interaction or effect modification. So the hazard ratio, the COGS model, actually allows you to put in something in there that will let you know whether something is an effect modifier or, in other words, causes an interaction. Okay? It sounds complicated, but this is actually a very common approach at the end of a clinical trial, because even if you randomize a whole lot of people and there is no possibility of confounding, let's say you have 5,000 people in each arm of your RCT, at the end of the day, there is not going to be confounding. They will equally distribute it in both arms. But you may want to know whether your treatment works equally well in men and women, depending on ethnicity or depending on whether they're diabetic or not, or whether the ejection fraction is very low or not. And in doing that, we're testing for interactions. And this is something you can do very easily with the COGS model. So the hazard ratio is the ratio of hazards. And as I said before, hazards are risk of an event per unit of time. Again, if you haven't had the event up to that point in time, what is the risk you are going to have it in the next unit of time? And the way we look at it is just the same as the relative risk. Less than 1 is a reduction in risk. Greater than 1 is an increase in risk. And if your confidence interval includes 1, you're not certain about your finding. It's the usual approach. But it's got advantages because, first of all, you can adjust for confounders, like we just discussed, but also it will have much greater power. And there are situations in which this is actually clinically very important. So this is just a brief example, real study in which people undergoing chemo or stem cell transplant, and the idea was to give them prophylactic platelet transfusions when their morning platelet counts were less than 10 times 10 to the 9th. So the primary endpoint was severe bleeding, bleeding with hemodynamic compromise or requiring transfusion up to 30 days after randomization. So Kaplan-Meier. No prophylaxis here, prophylaxis here, transfusing them with platelets or waiting for them to have an event. And this is a proportion of patients with the bleeding. You can see this is the opposite from what we saw before. Instead of plotting the people surviving free from the event, now we're plotting the probability of the event rate. It's the exact same thing. And this is not truncated. It's going from 0 to 1 or 0 to 100%. So this is not inflating the difference between the two of them. And this is the hazard ratio you're getting. So what is this telling us? So you start with the point estimate, which is 1.3, greater than 1, right? So when you're not getting prophylaxis, you bleed more, right? Based on the confidence interval, are we certain that that's a significant difference? Yeah, we're confident. Goes from 1.04 to 1.64, and the p-value is clearly less than 0.05. And when you look at the numbers at risk, they don't drop a whole lot. You do have good information. So this is a reliable graphic. That's the way you interpret this. Okay? First, you start with the visual impression. You make sure it's not inflated based on a truncated y-axis. It's not. You have pretty decent numbers down here. The hazard ratio, the lower confidence limit is not below 1. So p-value agrees with that. They bleed more when they don't get prophylaxis. So the adjusted hazard ratio was the one I just mentioned. But if you estimate the crude relative risk, and I did this, I didn't give you guys the paper, but if you actually look at the number of people who bled in each one of the two arms, this is what you get. You get 151 out of 301 in one arm and 128 over 299, which is actually 1.17. You see how this number is less impressive. In terms of percentages, what is the likelihood of somebody bleeding if they don't get platelet transfusion here in the adjusted estimate? Percentage-wise. Remember how you do it? No difference is 1. So you do 1.3 minus 1.3. That's 30% greater chance of bleeding if you don't get the platelet transfusion. Okay? So here, only 17% greater. So when you do a crude relative risk the way we usually do it, you may actually underestimate. Why? Because it's a relatively smallish trial. You start off with 300 people. This is not a mega trial with 5,000 people, and there may be characteristics for each patient that make them more prone to bleeding, and you couldn't really prevent confounding 100% because your budget was not enough to recruit thousands of patients. So the adjusted hazard ratio is probably a much better clinical estimate of the effect because it takes into consideration other causes for bleeding. You see that? Now, if you just did the crude relative risk, you will also have the problem that your lower confidence limit will be below 1. And you may be inclined to say, well, I'm not sure anymore. So you wouldn't reject the null hypothesis. Whereas if you take into consideration covariates, you will. So this is a great example of how the hazard ratio can have much better statistical power than the crude relative risk. So it's also more sensitive because sometimes you have an improvement in median survival, but at the end of the day, at the end of the overall follow-up time, maybe the proportion of people who survive is the same. And a very common example, sadly, is when you deal with palliative chemotherapy, any type of palliative treatment for cancer, because when the cancer is really devastating, you're going to have a very tiny proportion of people who are surviving progression-free. But if you introduce a new treatment that takes you from this blue line to the red line, you're increasing the median survival time. And believe me, if you're a patient who has this type of cancer, a few more months free from symptoms and enjoying the time with your family means a whole lot. If you do a relative risk over here, it will completely fail to capture this improvement in median survival that the hazard ratio is capturing. The hazard ratio here in this study was 0.3, whereas if you do a relative risk at 2 years, you only get 0.91. This is a relative risk reduction of 70%, and this is only 9%, and the lower confidence limit, shows a very good reduction, but this is not that impressive anymore. This is close to 1. So the hazard ratio in this case is far more sensitive to detect that improvement. Yeah.
In terms of like the time units that you're putting on those, on here it says risk ratio at 2 years. How do you think about hazard ratio in terms? Is it like per year?
The hazard ratio actually takes information from the very first day you start the follow-up all the way to the end. All that goes into the estimate of the hazard ratio. So it's actually looking at follow-up information for every period of time for which you had follow-up data, which actually begins the day after you randomize 1 participant to the study. So once you have 2 participants, one in each arm of the study, and you start looking at their survival, that's when you start estimating the hazard ratio. Whereas the relative risk, you just look at the number of people assigned to each arm, and you have the head count for the number of events, and it's a crude estimate. The other one gets much more information out of the follow-up data. So the thing to remember is that the hazard ratio will actually will incorporate the information from this early divergence going on to the much greater difference in median survival here in the graphic, and will continue to capture that difference along the follow-up. Whereas the relative risk is just taking a snapshot, a cross-sectional view over here. You understand? So we like the relative risk because in most instances when you're not dealing with palliative chemotherapy, and in good trials when the follow-up time is very similar in both arms and you don't have a whole lot of censoring, then it will be very close to the hazard ratio. And actually there are innumerable examples in which the hazard ratio and the relative risk are essentially identical. But in some instances, I just want you guys to be aware of the fact that they can be different from each other, and this is one of the reasons why. When both groups converge at the very end, but there is a median survival time difference, that it's meaningful to the patient. In some places where the resources are very limited, they may take a look at this and they may say, we don't have the money to pay for this new expensive drug as a society, so we're not going to try to, use our national health system to pay for it. But if you do have access to care and, you have means to pay for this for the individual patient, this is a meaningful difference.
So just a way to conceptualize it, is the hazard ratio sort of like the rate at which the event?
Absolutely.
Okay.
Absolutely. Because it takes into consideration the unit of time.
Okay.
Absolutely. Rates are events. So in other words, there is a more complicated way of doing relative risk in which you do events per person years of follow-up. I didn't even go there because people hate that and they fall asleep whenever I bring that up. And that's not what's expected from clinicians because you don't get that information from papers. They don't give you the person years of follow-up. There are a few journals like Lancet and BMJ, in the UK that require person years information in the abstract. But most American journals don't require that. So it's not likely that you'll encounter that in your usual randomized controlled trial report. Yeah.
In terms of additional adjustments, can we just assume that when you see hazard ratio, there's been some fancier footwork in terms of making that?
They will tell you it is adjusted, and they must tell you what they adjusted for. And there's, the beauty of now having online access to data is that now people post supplemental appendices that are huge. In the past, people will hide behind the fact that there's limited space in the journal to tell you, well, this is what I got, and you have to trust me. It's not that way anymore because I review papers for many journals, and what I tell people is, put that in your supplement because it's going to go online, and if people are interested in seeing what you adjusted for and what happened before and after the adjustment at each step of the way, they have the right to read that. So the information will be there. In any decent journal, the information will be there. So in other words, you're going to have an unadjusted result, and then they're going to tell you what they adjusted for, and if they adjusted for many things, it will be stepwise. So you're going to be able to see what made a difference, if any, when you incorporated new covariates. Like you can see if anything changes when you adjust for age, when you adjust by gender, when you adjust by diabetes, yes or no, or many other different covariates. So again, you can get the relative risk reduction estimate just doing 1 minus the hazard ratio, like you did for the relative risk. And there are ways of doing number need to treat from the hazard ratio. If you ever need to do that, I got a couple of programs that can do that for you. So any questions? All right, just email me if you have any questions, guys. Mark? I got it. Thank you. You actually really collectively, because I was thinking when you showed that slide that somebody would come up with that answer. It has to do, it's complicated. It has to do with the fact that we use degrees of freedom to adjust for the stochastic probability of finding. It gets a little complicated. But in essence, when you have the the approximated bell curve, it doesn't make a difference. Because if you have 600 participants and you divide any number by 600 or 599, it doesn't make a difference. But when you get into smaller numbers, you will always deviate from the bell curve. And I didn't want to get into that because, for example, if you toss a coin only 4 times, it is actually more likely that when you get to 1 or get to 0 than you get to 0. And actually, that's one of the ways they detect fraud in trading. Because people who randomly pick answers that know what they're doing tend to follow a pattern that in their mind would create an even spread probability. So, you know, there's this example, there's this person in UCSF, you know, this is by that Joel divides at the beginning of the year, she divides us into groups. And so the one group, you have to talk to them, physically do it, 100 times, write down the results. And tell the other group, I want you to make up results for talking. So the group that's making it up gets 50-50. And the group that's not making it up never gets 50. You get 51-49, 56-48. It's the same thing. When you start into the smaller numbers, there's something called the stochastic probability of events that deviates from the normal distribution. That's why we use n from 1. It has a huge impact for small samples, but no impact at all when you have huge samples. It's basically to not overestimate the probability that you use in a normally distributed curve. So standard, you know, the effect is that the standard deviation will tend to be much wider than you have smaller samples. I didn't want to go into that because it gets people confused, but the way to think of it is it doesn't make any impact when you have huge samples. Yeah. So, you know, the thing is about stats is that are you doing any research or are you trying to do research? So what have you been doing? Basic or clinical? It's clinical. Okay, so what variables did you look at?
We were looking for
All right. So how did you do your analysis or you guys got help from the statistician?
so the most recent work we did was actually
Okay. Okay, that's a different business.
everything else.
So, right, so that's a different business because we're just looking at agreement. Right. People usually don't understand kappa very well because they think in terms of just agreement, percent agreement, and that's not what it is.
Right.
Okay. No, but in terms of, you know, I was going to tell you about standard deviation and that. The beauty of having technology is that what you need to use are just concepts. With a good understanding of the idea, you can solve it. And the software does all the calculations for you. So you don't need to spend much time trying to think about, you know, the nitty-gritty, the nuts and bolts, if you understand what you're trying to do. So there are huge concepts like what type of variable I'm looking for. That will be hugely important to choose a test. And one of the huge problems I have is that many persons waste their time doing analysis with just t-tests and chi-squares and things like that. And then I look at it and like what you're doing, you know, many people instead of doing kappa will do percent agreement, and that's useful. So I'm glad you guys do kappa because that's much more important. All right. Very good. No problem. Yeah, it's supposed to be chronologically ordered these days. I actually like it better when I created folders for things, but for some reason the entire next folder that I made displays the
Yeah, I don't know what's happening. I don't like it though. Thank you. This actually isn't working. That's annoying. Well, no, just the Internet Explorer is so. Oh, I know. I use Firefox. There's Firefox. Just better in every way. Don't remember me, no. Too late. Oh, here, I'm just gonna get this booted up first. Yeah. Do I sign out? Oh, yeah, you probably need Firefox.
Thanks. I've only timed mine once, and I was a little long, so we'll see. Hi, guys. Oh. All right. Do you want to go first, or should I? Is it okay if we practice? Well, do you want to go first or second?
Okay. It's up to you.
All right. You can go.
Okay.
How is this the thing that you?
I don't know.
Yeah.
Oh, score.
Oh, it's nice. You can go back too. Oh.
Such fanciness. I wonder if presenter mode works. Nope. Haha! Got presenter mode to work. Ooh, there's a timer on this. Score. Okay, let's do this. Hi everyone, so today I'm going to be talking about mitochondria. Uni's on the slide, let's get started. So first off, what the heck are mitochondria? They're organelles that are possibly derived from endosymbiose bacteria, and there's some evidence for that. The double membrane is suggestive that they were endocytosed at some point. The fact they have their own genome and that it's circular, just like bacteria, Anyways, what are they for? Their main, but remember they're not their only purpose, is to generate ATP by first converting pyruvate to NADH, and then using that to generate ATP by creating a H+ gradient across the membrane, which it then uses to generate the ATP. So first big question about mitochondria, where do they get their proteins? Some are produced internally, but most are not. Most are produced in the cell cytosol and are derived from nuclear DNA and are then imported via TOM and TIM. And these proteins that are produced in the cytosol are signaled for a mitochondrial destination with an N-terminal signal. So it's at the N end of the protein. So how are they imported? You've got TOM, which is transporter outer membrane, so it's right in the name, and it recognizes an N-terminal signal sequence on the protein and starts threading it through. Then TIM, which is lined up with TOM after it's recognized the protein, threads the protein through the inner membrane. It's important to remember that these proteins can be released into either membrane or into the matrix. And so let's go through that process kind of step by step. So first off here, you've got the nuclear protein signal. The N-terminal signal is bound by TOM. TOM then lines up with TIM once it's got the protein bound, and then the protein is threaded through. And remember, it can be stopped at either membrane and inserted. If there's an internal to the protein, there's a stop signal, which tells it to let it go into the membrane. Otherwise, it's threaded all the way through where it's bound by HSP, or heat shock proteins, folded, and then the signal sequence is cleaved. Next up, electron transport chain. First, there's a couple preliminary steps. Remember, pyruvate is produced by glycolysis in the cytosol. I'm sure someone's already been over this, but I'm going to review it anyways. That pyruvate is then imported into the mitochondria, where it's converted to acetyl-CoA by pyruvate dehydrogenase. And that acetyl-CoA is what's run through the Krebs cycle. The Krebs cycle, remember, it happens inside the mitochondria in eukaryotes. This is the Krebs cycle. I would not worry about memorizing individual steps, mostly focus on the big picture. One pyruvate, which is converted to acetyl-CoA, then in the end gives you 3 NADHs and FADH2, and also a GTP. On this slide, it's ATP. It's actually GTP, but they're basically interchangeable, so it's really not that important. 3 NADH, 1 FADH2. Electron transport chain. So what's the overall goal? We're trying to use electrons that are donated from NADH to reduce oxygen to water, and in the process, and use that energy to pump hydrogens across the membrane. Then we use that hydrogen gradient to convert ADP and phosphate to ATP. So let's look at a pretty picture. So here's the picture of, and remember, it happens in the internal membrane of the mitochondria. Starts, NADH donates its electrons in. That pumps out a hydrogen here. And remember, hydrogens are pumped out at complexes 1, 3, and 4. Another thing to note is that FADH2 starts a little later in the process at complex 2, or succinate dehydrogenase, so it doesn't result in quite as many hydrogen ions being pumped out. And then finally, don't worry about each individual step, but at the end you're reducing oxygen to water, and that's just great. So in text format, NADH donates its electrons into complex 1. FADH2 donates its electrons into complex 2, aka succinate dehydrogenase. Then they go through complex 3, cytochrome C, complex 4, where the oxygen is reduced to H2O. And throughout this process, we're pumping out hydrogens. Now we need to use those hydrogens to produce ATP, and we do that through complex 5, which uses the electrochemical gradient, which pushes hydrogens across the membrane and actually turns complex 5. So it actually literally revolves. And the physical forces from this push ADP and phosphate together, making ATP. Here's a picture. So you've got the pore, the hydrogens flow through, and it's coupled to a rotation mechanism that actually forces ADP and P together. 3 hydrogens for every ATP. Don't worry about the accounting. In summary, use pyruvate to produce reducing equivalents, NADH and FADH2. These then donate their electrons in, which is used to pump hydrogens across the membrane at complexes 1, 3, and 4. Then the hydrogen gradient is used to produce ATP. That's the end of the electron transport chain. Moving on to